Chapter 5, Section 5.4, Trigonometric Functions of Real Numbers, Periodic Functions. In this sequence of PowerPoint slides, we'll discuss the unit circle definitions of the trigonometric functions. I'll also show you how they're consistent with the right triangle definitions. We'll recognize and then later use the domain and range of the sine and cosine function. And we'll discuss even and odd trigonometric functions and periodic properties. Unit circle. Unit circle, as we discussed in the previous PowerPoint slide, is a circle of radius 1 centered about the origin. So the equation of the circle centered about the origin is x squared plus y squared equals r squared. And with r being 1, then 1 squared is 1, so the equation of the unit circle, as shown here, is x squared plus y squared equals 1. So let's get a quick sketch of the unit circle here. Okay, if the radius is 1, then this point here on the unit circle, its xy coordinate would then be 1, 0. Since the radius is 1, from here to here is also the radius of the circle, so that makes this coordinate here 0, 1. And then over here, this coordinate would be negative 1, 0, and this coordinate here would be 0, negative 1. So this is 0 or 2 pi, dependent upon whether you start or end at that spot. This is pi over 2. This is pi, and this is 3 pi over 2. And just having the coordinate any one of these would indicate it's the unit circle, but often we write its equation there, x squared plus y squared equals 1, to indicate that it is the unit circle. Okay. We'll refer to this diagram throughout the discussion. In a unit circle, the radian measure of the central angle, that's the central angle here marked as t, is equal to the length of the intersected arc. This is the length of the arc right here. Both are given by the same real number t. So what this is saying is that radian measure occurs when you have the length of this arc equal to the value of this angle. That then is considered to be a measure of 1 radian. So a measure of 2 radians would be where this length of arc is twice the measure of this angle given by the real number t. As you can see by the picture, this is drawn to scale. 1 radian is rather large. Turns out it's about 57 degrees. So there are 2 pi radians in the circle, so in other words there are only 6.28 radians in the entire circle. This would be pi, so this would measure 3.14 radians, and this is roughly 3.14 divided by 2, or 1.57 radians. So 1 radian is rather large. As we discussed earlier, the relationship between the arc length, s, the radius of the circle, r, and the central angle theta is given by s equals r theta. Now, if we're in the unit circle, then r is equal to 1. So on the unit circle, the arc length is equal to the central angle. But here, in the figure, they use the value t. So theta is given by t. So s is equal to t. And that's what it's saying here, that 1 radian is defined to be where the arc length, s, is equal to the angle subtended by the real number t. Let's look at the definitions of the trigonometric functions on the unit circle. Previous PowerPoint discussion, I said always think of the sine being the y-coordinate of point P, and the cosine being the x-coordinate of point P. Now here we have sine of t being exactly the y-coordinate, and why is that consistent? Well, Since we have a unit circle of radius 1, we have point P. Let's suppose it's here. So P has coordinates x, y. We say that sine of t is the y coordinate. Okay, so here then is the measure of t. So that amount there is your measure of the central angle t. Why is that the y coordinate? Well, the radius here is 1 because this is the unit circle. Unit means a value of 1. So since it's the unit circle, the right triangle definitions, sine t is opposite over hypotenuse, would work out because the opposite here is this length, which is given by the height of point P above the x-axis, that's y. The hypotenuse is the radius of the circle. Y over r was the previous definition, but r is 1, so it works out that sine t is just the y coordinate. So in the unit circle, things are greatly simplified. The sine is not y over r, it's just y. Cosine of angle t is given by just the x-coordinate of point P, not x over r, because r is 1. Tangent is still y divided by x, and these three functions are still reciprocals of these three as they were before, but it's simplified, and that's why we work on the unit circle. By the way, anything that is not on a circle of radius 1 can be made to be put on a circle of radius 1, and we say that we unitize that length. So I'll give you an example of that at some point. The domain and the range of the sine and the cosine function. Okay, so the domain are the inputs and the range are the outputs. So if we're looking at, say, the sine tracks the y-coordinate. So let's put the unit circle here in view. We track the y-coordinate, we see that the y-coordinate varies from 0 to 1 to 0 to minus 1 back to 0. So the full values that the sine function undergoes within one rotation fluctuates between plus and minus 1. So that's why the range of the sine is plus and minus 1. The cosine's the same. Cosine varies from 1 to 0 to negative 1 to 0 back to 1 again, because cosine tracks the x-coordinate. So it too undergoes a full range within one rotation of negative 1 to 1. The domain can be any real number because the larger the number just means the more we rotate about the circle. So the domain is unrestricted, but the range is always between plus and minus 1. So another way to say this is to say that the sine of t is always between plus 1 and minus 1, and the same thing for cosine is between plus 1 and minus 1. So that's a different way to say the same thing as it says here. Range is restricted between plus and minus 1. Okay, even and odd trigonometric functions. Well, recall the definition of even function to be that a function is considered even if f of negative x is the same thing as f of x. An algebraic example would be like y equals x squared. So replacing x by, say, 2 or negative 2 yields the same value of y. That means that it has symmetry about the y-axis. Now, trig functions can also be even and odd. Turns out that the cosine and its reciprocal are even functions. See, f of negative t is the same as f of t. So it's the same relationship here. Now, why is the cosine an even function? Okay, so consider it like this. If we rotate, let's say, pi over 4, so So there's your value of t. Then the coordinates of point P here are root 2 over 2 and square root of 2 over 2. And of course, the cosine of pi over 4 tracks the x-coordinate, so that's root 2 over 2. Now, if you look at the negative angle here, negative pi over 4, suppose that is t. Well, that puts you on the circle at this place for point P. Well, it's still the same angle. It's a pi over 4 angle. So the angle, if you wish, within the triangle, if you want to think about it like that, is still the same. So the lengths of the sides are the same. In other words, the coordinates of point P are the same, except that you're in the fourth quadrant. So the coordinates of point P here are positive for the x-coordinate, but negative for the y-coordinate. So we try to find the cosine of negative pi over 4. Well, cosine tracks the x-coordinate, and the x-coordinate is still positive square root of 2 over 2. So the cosine of negative t and the cosine of t have exactly the same value, because cosine tracks the x-coordinate, and in these two quadrants, the x-coordinates are both positive. Now, for larger values of t, let's say a value that swings you over here to the second quadrant, now cosine would be a negative value, but the opposite angle will swing you in the third quadrant, which again, the cosine tracks the x-coordinate, is negative here as well. So you get the same value of that angle, even if you're larger than 90 degrees. Okay, now all the other functions are odd, and why are they odd? Well, we can see here by the diagram. Suppose that we replace cosine with sine here. The sine of pi over 4 is the y-coordinate, so square root of 2 over 2. But if we look at the negative angle, sine, which tracks the y-coordinate, look at the y-coordinate at negative pi over 4, because we switched quadrants, now we're below the x-axis, the y-coordinate's negative. So the value is the same, but opposite. And that means odd function, right? Because a function is odd if f of negative x is the opposite of f of x. And that's what it's saying here. F of negative t is equal to negative f of t. So they're odd. Well, if the sine is odd and the cosine is even, then the tangent, which is sine divided by cosine, or y divided by x, is odd divided by even, which also works out to be odd. If the sine is odd, its reciprocal function is odd. And if the tangent's odd, its reciprocal function is also odd. So that's why that works out like that. Okay. What does it mean for a function to be periodic? It means that after a certain value, here we have it denoted by p, we get a repetition of all the values again. In other words, it cycles through the same values all over again. So, for instance, you take the tides, and it takes 6 hours for the tide to come in and 6 hours for the tide to go out. So it takes a total of 12 hours. P would be 12 for the tide. After that, it cycles through again. Tide comes in, then it goes back out. And that takes another period, P. And then again, it cycles through that again. So anything that undergoes repetitive motion is called a periodic function. That would include something bouncing up and down on a spring. That would include a piston moving inside the cylinder head. It would include a pendulum swinging back and forth, a clock as it rotates around, cycling through the same values, or trig functions. Because once we take the unit circle and rotate about that circle once, we obtain all the values between plus and minus 1 for sine or cosine. And then again, if we go around the circle, we cycle through those values again. So the period of sine and cosine would then be 2 pi. In fact, the periodic properties are next to discuss. That's what it's saying right here. The period of the sine f of t plus p equals f of t, because after 2 pi, you're back to your starting point, and the cycle begins all over again, and you'll generate the same values again. Same is true for the cosine. It takes a full rotation about the circle, or 2 pi, for the sine of the cosine to recycle through its same values. So we say the period of sine and cosine is 2 pi, whereas the period of the tides would be 12 hours. Now the tangent and the cotangent do not have period 2 pi. They have period pi. That's a little tricky because these are ratios, right? The tangent's y over x. In this quadrant, the tangent's positive. But in this quadrant over here, because it's the ratio of y to x, it's also positive. So that is pi, 180-degree rotation, apart. In this quadrant, negative, positive, the tangent's negative. And in this quadrant, positive, negative, the tangent is also negative. And they are 180 degrees apart. So the tangent has period pi. It recycles through its values after only, you could say, a rotation of pi, whereas the sine and cosine take an entire cycle about the circle in order to repeat. Okay, this is more of the same. The repetitive behavior of the sine and the cosine, well, the period is 2 pi, so after 2 pi, the cycle begins again. But there's no reason why we can't continue to cycle through those values again and again and again. So what this is saying is any multiples of a full rotation have no effect on the value of the sine, or multiple rotations about the circle have no effect upon the cosine, because you're just going to cycle through those values again. So it's not just one time that we travel around the circle. We could go around that 1,000 times, and once again we'd be cycling through the exact same values again. So multiple periods, sine of t plus multiple periods of p, or cosine of t plus multiple periods of p, just give the original function back. Now with the tangent, since the period is pi, we have multiple values of pi, multiple periods, t plus multiple periods of p, and that's still equal to the tangent. And again, I'll do some examples in the problem area that help make this a little bit more clear. So that's all for section 5.4 PowerPoint slide.